Okay, so today's plan is going to be on naming ionic compounds. Now, we haven't talked about this word right here yet, ionic. We haven't talked about what an ionic compound is, but last class we were looking at certain types of compounds, namely how to name them, as well as how to find their formulas. We're just going to focus on naming today, and for a certain type of compound, let's get started. So like I just said, last class, we took our first look at chemical formulas and chemical names. Formulas use the symbol for each element that makes up the compound. So for example, Mg3N2, that was 3 magnesium and 2 nitrogens. That's what makes up that compound. Now, chemical names express what elements make up that compound. They don't necessarily tell us how many of each element is in the compound, though. Also, they typically end with "ide." So an example that we would have dealt with perhaps yesterday was magnesium nitride. That's actually, as a matter of fact, the exact same thing as what we showed in this example right here. This one was the formula, and then this one is the actual chemical name. Now, I want you to really look at that ending, that "ide," right? Nitride. There isn't an element literally called nitride, but there is, of course, nitrogen. Just when you name compounds, though, typically you just cross off the ending to it and you end it with "ide." And you basically just cut it wherever it sounds good, like as simple as that sounds. Like you wouldn't say nitroide, that just doesn't roll off the tongue, or you wouldn't say nitrogide. It doesn't work, right? Nitride just seems to sound better. If it sounds right, it typically is right. We'll get into that later on, though. We don't have to worry about that for now. Today, though, we are going to look at how to write the chemical names for a certain type of chemical compound. There's different types of chemical compounds. We'll get a little bit into that today as well, but we'll just look at one specific type. Matter of fact, it's what I hopefully would think is a little bit of the easier type, just to kind of get a warm up with this. But anyway, let's get started. Before we begin, though, before I go any further, I should kind of tell you right now, you might want to get a periodic table out. You're going to be using a periodic table a lot today. If you haven't already got your periodic table out and ready to go, you're going to want to make sure you have that. Anyway, let's get rolling. Before we really begin, though, I need to start by reminding you about protons, electrons, and neutrons. We talked about this for the very first time when we first looked at our periodic table. This was the first thing we were looking at with it. So I want you to recall when we originally learned about the periodic table, how can we tell how many protons, electrons, and neutrons an element has? Let's actually look at a more specific example first. How many of each, protons, electrons, and neutrons, would an atom of cobalt have? Take a look at your periodic table, see if you can scan the periodic table right now, and see if you can find where cobalt is. Once you've found cobalt, I want you to think about how you can tell how many protons, electrons, and neutrons it has. So if you need a little bit of help finding cobalt, I'm just going to draw its little box right here. Cobalt is kind of in the middle of the periodic table, up on the highest row that it is in there. I think it's on row 4. Cobalt has CO as its chemical symbol. It has 58.6 down in the bottom, and it has 27 up in the corner. What those numbers mean is this number up top is what we call its atomic number. Atomic number. This number down here is what we call its atomic mass. Literally just tells you how heavy it is, basically, right? We actually use these two numbers to help us determine protons, electrons, and neutrons. Now, for atoms, just singular atoms, the number of protons is just equal to your atomic number. So for cobalt, the number of protons would just be 27. Now, electrons are actually quite nice. They're exactly the same as protons, as long as you have an atom. There's something else that we're going to introduce today where it gets an electric charge. So in other words, the number of electrons will change. But for a single atom of cobalt, it's going to have the same number of electrons. And this is because atoms are electrically neutral. Protons were the positive piece, electrons are the negative piece. We want them balanced in an atom. We want there to be no overall charge, positive or negative. So in other words, long story short, the number of electrons is 27. Now, neutrons are a bit of the wild card here. Neutrons take a little bit of math to figure out. Neutrons require us to look at the atomic mass and the atomic number. And what we have to do to these two things is we have to take the atomic mass and subtract the atomic number from it. So in other words, we need to go 58.6 and we need to take away 27. What this is going to give us is it's going to give me 31.6. Now, here's the trouble. You can't have 31.6 neutrons. Neutrons are a physical thing. You can't just have a decimal number of them. So what we do is we actually just round up to the nearest whole number. This might seem a little Mickey Mouse, like it seems kind of like a funny way of doing this, but that is generally how it works. You just round your atomic mass after you subtract the atomic number, of course. You just round the atomic mass to the nearest whole number. So that's going to be 32 neutrons. So just as a recap here, the protons and electrons, as long as it's an atom, you're going to have the same number of each. As for neutrons, you have to use the mass minus the number. Anyway, that'll be a little important today. We won't really have to find protons, electrons, and neutrons, but I want you to keep it in the back of your mind that for atoms, the number of protons is equal to the number of electrons. In other words, they're electrically balanced. There's not an overall charge. Here we go. So getting into chemical compounds, I want you once again to take a look at your periodic table. I want you to notice that the left half of your table, all the ones that are in green, those are your metals. The right half of your periodic table, I shouldn't even call it half, it's more like the right third of it or something. Those are your nonmetals, the ones that are kind of that orangey peach kind of color, right? Now, this is one of the primary ways that the periodic table is organized, literally just metals versus nonmetals. It's organized quite neatly along those two lines. Then we have the purple section in the middle. Those are the metalloids. We won't worry about those too much because they can act a little bit like a metal and a little bit like a nonmetal. They just complicate things for us. But overall, that periodic table is more or less organized as metals versus nonmetals. Now, chemical compounds, this is where we take two or more elements. So you pick two or more things on your periodic table and you stick them together. They can also be categorized using metals versus nonmetals, but it doesn't work quite that easily. We actually have special names for them when we categorize compounds using metals and nonmetals. The first one, and the one we're going to be more worried about today, are ionic compounds. Ionic compounds are compounds that contain one metal and one nonmetal. So in other words, an ionic compound, two or more elements, right? An ionic compound is going to be one of your metals, one of the ones in green, combined with one of the ones in that orangey pink kind of color, right? That is going to be an ionic compound. Now, the way I always remember ionic as being a metal and a nonmetal is I take a look at the word ionic, and then I think, okay, ion, it kind of almost looks like iron, and everybody knows that iron is a metal. That's just how I always remembered it. It's pretty stupid, but it worked, right? The other kind of compound, which we're not going to deal with today, but we're going to deal with in a few days, are molecular compounds. Molecular compounds, right? Molecular compounds, they don't contain any metals at all. They're just nonmetals. They're just nonmetals that have stuck together with one another, not a single metal involved. Now, you might be wondering, what about when you have like two metals together, like a metal combined with another metal? That's not really a thing. The closest thing that we can get to that is something called an alloy, which is more of a mixture rather than an actual chemical compound. An alloy is where you mix two molten metals together. So, for example, the most classic example is mixing copper and tin. If you mix copper and tin together, when they're melted, it blends together and forms bronze, right? That's not a chemical compound, though. That's an alloy. It's something a little different. The only ones we need to understand, though, are ionic compounds, which is a metal and a nonmetal, and molecular compounds, which just are two nonmetals. In other words, no metals at all. Again, we're only going to focus on ionic compounds for the next few days. Molecular compounds will come around in a little while. So we're focusing on when we take one metal and one nonmetal today. Keep that in mind. All right, so ionic compounds, metal and a nonmetal. What's so special about them? What do we care? What do they even look like, right? Well, here's some examples. Ionic compounds, generally speaking, are solids at room temperature. In other words, they're not going to be a liquid, they're not going to be a gas. Ionic compounds are solids at room temperature. Ionic compounds are also good conductors of electricity. Now, that's to varying degrees. Some of them are better at conducting electricity than others, but all of them do have some electrical conductivity to them. Now, ionic compounds also have a crystal shape to them, at very least at the microscopic level. There's some obvious crystal shaped ones like sodium chloride, NaCl. Sodium is a metal, chlorine is a nonmetal. When they combine together, it actually just forms table salt, right? Table salt clearly has a crystal shape to it. It's also a solid at room temperature, and at least if you dissolved it in water, it's a really good conductor of electricity, right? Oh, and speaking of dissolving water, that's a fourth point, soluble in water. In other words, they'll dissolve in water. Now, another kind of ionic compound would be magnesium oxide, which is this white powder right here. Magnesium, of course, is a metal, and then oxygen, of course, is a nonmetal. So magnesium oxide is an ionic compound. Now, if you look at that picture there, it looks literally just like some white powder. If you were to look at it under a microscope, though, you'll notice the individual little pieces of this white powder actually have a crystalline shape to them, right? So ionic compounds, they have those 4 different properties. We'll get into that a little later. Our focus for today is we'll want to try naming these, right? Now, why are they called ionic? My little rule earlier where I said, oh, it looks like iron, that's not really why. That's just something that helped me remember. Here's why they're called ionic. An ion is an atom that has either a positive electric charge or a negative electric charge. So if you were to take a single atom and give it a charge, whether it's a positive charge or a negative charge, it would become an ion. Now, metals are kind of funny. Metals generally like becoming positively charged. It's just how they behave. Generally speaking, they want to become positive. What this means is they like to give away one or more of their electrons. Remember, electrons with a negatively charged piece. So if you give away a negative, you're becoming more positive. And that's what metals like to do. Non-metals, on the other hand, they actually like becoming negatively charged. This means they like to receive one or more electrons, right? If you receive electrons, you're becoming more negative because electrons are negatively charged. Now, you might be wondering, well, how many electrons does it give away or take in, right, when they become positive or negatively charged? Well, that's that other number on the periodic table that we haven't used yet. You'll notice in the top right corner of every single element, or at least almost every single element, there's a number and then either a plus sign or a minus sign. Let's look at aluminum, for instance. Aluminum, atomic number 13, it's kind of over closer to the right side. It actually has +3, or 3+ is how it's written actually, 3+ written in the top right-hand corner. What this means is when you have aluminum, if it becomes electrically charged, it likes to have a +3 charge to it. In other words, it likes to lose 3 electrons. Now, I know lose and positive seem like a little backwards to one another. That's just a hurdle we'll have to get through. But +3 means it's lost 3 electrons, become more positive. Oxygen, on the other hand, a classic non-metal, has a 2 negative charge, right? In other words, it likes to gain 2 electrons. It wants to get more negative pieces to it, right? Those ion charges are going to become really important in the next couple of days. We're not going to use them too much today, but they still are pretty important. Now, so again, gaining, losing electrons, like we just said, oxygen has a 2 negative charge. That means it gains 2 electrons. In other words, it becomes more negative. Now, the general rule, this is just kind of nice to know, a general rule is that an element likes to gain or lose enough electrons that it becomes similar to the nearest noble gas. Remember noble gases, we talked about that a little bit. Noble gases are the furthest right group, in other words, furthest right column on the periodic table. It's things like helium and neon, etc., right? Those are the noble gases. The noble gases, if you were to look at your periodic table, they actually don't have any charges to them. That's because noble gases do not like to change. Noble, like as in like a king, noble, oops, oh my goodness, change slides. Kings are noble, right? That's where the word noble comes from. They think they're the best, right? So noble gases think they're the best. They don't think they need to change. That's where we're at with those. Anyway, let's move on. Cations and anions, as if it wasn't enough that I was already telling you a bunch of other things, there's a couple more pieces of terminology you need to know. An ion that loses electrons, in other words, becomes more positive, is called a cation. An ion that gains electrons is called an anion. Metals, of course, generally become cations because they have a positive charge. Positive charge, right? They're cations, positive charge. Non-metals generally become anions. I haven't got a smart, clever thing to say about that, so I just say anion, kind of sounds like onion, and onions are pretty negative. They smell pretty bad. That's all I got to say about that. Anyway, moving on. Ionic compounds. Now, the entire point of gaining and losing electrons, the entire reason we've been building up to this, the entire point of gaining and losing electrons is so that elements can bond with other elements. In other words, they can merge, they can hold hands, they can join together, they can sing, they can dance, they can do all those things, right? The electrons, however, when they are given or taken away, they don't just disappear. They just get transferred to other elements, which creates an ionic bond. So in this animated picture that we're seeing right here, it's just going to loop again right now, you're going to see sodium and fluorine. Sodium is a metal, so it loses an electron, gives it to fluorine, a non-metal, which likes to gain an electron, and in doing so, they're now bonded together. It's kind of like getting like married or something. It's like, all right, here's your ring, bingo, bango, bongo, forever together, no big deal, right? That's how ionic compounds work. They give or take electrons away from one another, and they get stuck together because of that. That bonds them together. They don't just lose them completely. They just bond together with this shared electron that they've given or taken from one another. So again, ionic compounds are compounds formed between two or more ions. All ionic compounds need to have a cation, the positive piece, that'd be sodium in this case, bonding with anions, the negative piece, which in this case would be fluorine. Now, the other really important thing, I cannot stress this enough, the sum of all the charges in an ionic compound needs to equal 0. Notice in this one's becoming 1 positive, and this one's becoming 1 negative. It gained an electron, and this one lost an electron. Positive 1, negative 1, balanced out to equal 0. Okay, so those two numbers need to equal 0. Positive 1 and negative 1 equals 0. Really important. We'll come back to that in a bit again today. Now, just as a little bit of recap, how do you know if it's ionic? If you were paying attention, you'd already have the answer to that. But here it is. In general, you can tell a compound is ionic if there is a metal bonded with a nonmetal. So a metal and a nonmetal, that makes an ionic bond. And the metal is usually the cation, the nonmetal is usually the anion. Matter of fact, I go further than usually. In this course, I think it's pretty much all the time. Now, let's have a look at this. You're going to need your periodic table for this because I doubt that we know whether we know our metals and nonmetals, at least right off the top of our heads. Which of the following compounds are ionic? I suggest we pause the video here, give these 3 a try on your own, and we'll go over it together in just a second. Okay, I'm going to go over it together now. Hopefully you're able to find each of these. This first one, NaCl, sodium and chlorine. Sodium is actually metal. Chlorine is a nonmetal. So a metal and a nonmetal, guess what? That's ionic. Perfect. Next one, H2O. You probably know that's water, right? H2O, hydrogen, which is way up in the top left corner, that's a nonmetal. And oxygen, which is kind of over on the right, is also a nonmetal. Guess what? That's not ionic. That's what we would call molecular. You didn't have to write molecular, but I'm going to write it anyway. It's a molecular compound. Last one, FeO. That's iron and oxygen. Iron, of course, is a metal. Oxygen is a nonmetal. Guess what? That one's ionic. Hopefully it makes some sense, right? You have to use your periodic table. You have to look at each of your elements and figure out whether they are metals or nonmetals. Anyway, moving on. All right, here we are. This is the cream of the crop right here now. This is what we really were building to today. Naming ionic compounds. Ionic compounds aren't usually too tough to name. Keyword there, usually, right? Sometimes they can be. Here's what you got to do to name an ionic compound. Step 1, write the element name of the cation. In other words, the metal. So always list your metal first. You'll notice on that last slide there, we listed the metals first on the 2 ionic compounds, right? This one and this one, the metal was listed first, although these were formulas, not names, but it is what it is, same idea. List the metal first, that's what I'm trying to get at here. So list the element name of the cation, the metal, then write the element name of the anion, in other words, the nonmetal, but change the ending of that nonmetal to "-ide". All of these compounds, they always have to end with "-ide". If it doesn't end with "-ide", it's not a compound, right? You have to end it with "-ide". That's it. That's all you got to do. Really, it's just a 2-step thing, believe me, right? So write the name of the metal and then write the name of the nonmetal, but change the ending to "-ide". Keep in mind, some anions are awkward to change to "-ide". I kind of referred to that earlier today. Oxygen is not oxygenide, right? That just doesn't sound good. They change it just to oxide, okay? Phosphorus is phosphide. It's not phosphoruside, right? That just sounds like too much. It's phosphide. Usually, if it sounds right, it is right. There is a little bit of a learning curve with this. We'll get to it as time goes on. If you make some mistakes early on, that's okay. Just generally speaking, think about what sounds right. I know that's a very stupid kind of Mickey Mouse thing to say, but it is actually pretty true. Like sulfur, for instance, is not sulfuride, it's sulfide, right? Carbon isn't carbonide, it's carbide. Anyway, moving on. Let's name these ionic compounds. We're going to do these 3 together. We're not going to pause here. Let's look at this first one, MgO. First, identify the metal and the nonmetal. Magnesium is Mg. If you didn't know that, of course, use your periodic table. Mg is magnesium. That's a metal. So we're going to name the metal first, just literally just magnesium. You don't put "-ide" on the metal. It's just magnesium, straight up magnesium. And then we have oxygen. So oxygens are nonmetal. We have to write our nonmetal now, but change the ending to "ide." So it's not oxygenide. It's going to be oxide. Magnesium oxide. Done. Right? Next one. NaF. Na is sodium. F is fluorine. Sodium is a metal. Fluorine is a nonmetal. Name the metal first. So the metal is sodium, and the nonmetal is fluorine. So it's not going to be sodium fluorine. It's not going to be sodium fluorinide. It's going to be sodium fluoride. Spelling can be a bit of a weird one here too, but do your best, right? Last one, KCl. K is kind of a funny one. K is actually potassium, right? K is potassium, and even weirder, because probably what you think of potassium, you probably say, oh, well, potassium is in like bananas and stuff like that. That's at least what I think of when I hear potassium. But potassium is actually a metal, right? So we have a metal, and chlorine, of course, is a nonmetal. So we have to write the metal name first. I'll write it again, potassium. And then we have to change the ending of the nonmetal to "ide. So it's going to be not chlorine, and it's not going to be chlorinide. It's just going to be chloride, potassium chloride, right? Again, whatever sounds right, generally speaking, is right. That's, again, as good of an explanation as I can give. Over time, you'll get the hang of it for sure. Okay, we have one last thing to get to today. I didn't want to get to this because it just seems like too much. I apologize, but this is the last thing we got to work with. Sometimes there are ions, in other words, metals, cations, I should be more specific at. Sometimes there are ions that have more than one possible charge. These examples could be like iron or copper or lead. There's a whole bunch of them. Most of them are metals. Your nonmetals, there's a couple on there that have positive charges. Like I see sulfur and selenium have positive charges mixed in there. You can ignore the positive charges on your nonmetals. They don't really do anything. But anyway, these elements that do have more than one possible charge, namely the metals that have more than one possible charge, we call them multivalent ions. There's a name. Try saying that 10 times fast. Multivalent ions. Now here's the issue. If someone wrote iron oxide, so you mixed iron with oxygen, you got iron oxide. Just by looking at that name, we wouldn't know what charge it has. Iron could either have a 3 positive charge or a 2 positive charge, right? So we wouldn't know what charge it has. So for elements that have multiple charges, for these multivalent ions, we have to use Roman numerals in the name to indicate the charge. So this can actually make a dramatic difference in what actually forms. Iron 2 oxide is actually like a black powdery kind of thing, whereas iron 3 oxide is this reddish brown stuff. Matter of fact, iron 3 oxide is literally just rust, right? It's what we call rust, iron 3 oxide. But those are chemically two different things. One of them has a 2 positive charge in the iron, and the other one has a 3 positive charge in the iron, right? It is really, really important that you name each one, because it they do mean different things. Now we'll get into telling like, oh, which one has which charge a little later. I just want you for now to know that these exist, right? There's some compounds that have more than one possible charge. This is just because they can be charged 2 or 3 different ways, right? Not the end of the world. So let's do a couple multivalent ion examples. Oh, wow, yeah, we are really jumping to this. So remember, when you have an ionic compound, two things put together, a metal and a nonmetal put together, the overall charge of that ionic compound must always be equal to 0. Your positives need to balance out with your negatives. Let's name the following. We have NiF3. So Ni is nickel. If you look at nickel on your periodic table, you're going to see that it has either a 2 positive charge or a 3 positive charge. Shoot, right? There's more than one kind, right? And if we want to name this, we have to figure out which one it is. Well, let's have a look at fluorine. We have 3 fluorines here. If you look on your periodic table, you're going to see that fluorine has a 1 negative charge. But notice we have 3 fluorines. Since we have 3 fluorines, the overall charge of your fluorines is 3 times -1, which is -3, or 3 negative, as we write in chemistry, right? I don't know why it is backwards in chemistry like that. It's just is what it is, right? It's not the same as math, but it's the same idea, right? Anyway, overall for our fluorines, we have -3. We only have 1 nickel, right? The overall charge of this compound has to be 0. So what do you think it is? Do you think it's going to be +2, or do you think it's going to be +3? Well, hopefully you can see, since your fluorines are 3 negative, your nickel has to have a +3 charge to balance that out. In other words, to make it equal to 0. So our chemical name We have to use Roman numerals because nickel is one of those weird multivalent ions that has more than one possible charge. We're going to use Roman numerals here. So we're going to say nickel, that's the metal name, then 3 using Roman numerals, because that's telling us what charge the nickel is, and then the non-metal name ending with "ide." So that would be fluoride. Nickel 3 fluoride, right? That would not be the same thing as nickel 2 fluoride. Those are two different things. Let's look at our next example. Cu3N2. So we have 3 of these. Cu, by the way, is copper. So we have 3 coppers and we have 2 nitrogens. Now here's the thing. If we look at copper on the periodic table, you're going to see that copper can have a 1 positive charge or a 2 positive charge. Now the number of copper we have is going to be important here, but also what's important is the number of nitrogen that we have here. If you look at nitrogen on your periodic table, the charge that it has is either 3 negative or 5 positive. Now I'll tell you this much, with your nonmetals, they're always going to have a negative charge. So you can ignore that 5 positive there. That's not even going to be possible. So we have to say that our nitrogen has a 3 negative charge. But wait a minute, there's 2 nitrogens there. That means the overall charge of our nitrogens is going to be 2 times 3 negative, which is 6 negative. So we have a 6 negative charge on our nonmetal. Now, if you look at our copper, we have 3 coppers. Now we have to figure, is that going to have a positive 1 charge for each copper or a positive 2 charge for each copper? Remember, we have to balance out a negative 6 right over here. So let's think. If we had 3 positive ones, we would only have a positive 3 charge. But if we had 2 positive charges, 3 times 2 is positive 6. That tells us we have to use the positive 2 charge. So in this case, because we have to use the positive 2 charge to keep this balanced and equal 0, we have to say it's copper, and then 2 is our charge, so 2, and then our nonmetal name, nitride. Copper 2 nitride. That would be the name of that one there. All right, a little bit weird. So again, just bear with me on that. Last one, PbO2. So Pb is our first element there. If you scan your periodic table, you're going to see that that's actually lead. Lead's kind of got a weird symbol, right? Now, if you look at lead, wonders never cease here. It either has a positive 2 charge or a positive 4 charge. We got to figure out which one it's going to use, right? In order to do that, let's have a look at our oxygen. If you look at oxygen on the periodic table, you're going to see that the only charge that oxygen can have is 2 negative. So 2 negative is our charge for oxygen, but we have 2 oxygens here. So the overall charge of our oxygen is 2 times negative 2, which is negative 4. Now let's go back to our lead now, Pb, right? There's only one of them here. So we need one of these leads to balance out the positive or the negative 4 charge, right? To balance out the negative 4 charge, I kind of just gave it away. We need the positive 4, right? So this is going to be lead, and then 4. Remember, with Roman numerals, it's not literally just going to be 4 lines. 4 is actually like IV, right? It means like 1 before 5. That's just how Roman numerals work. So lead, 4, and then our nonmetal name ending in ide, so oxide. Lead 4 oxide. Wow. Okay, so that was a long lesson. I apologize. I think I kind of gave you guys a warning at the beginning. But to recap, just because we learned a lot, what are ions? Think about that for a second. What is an ion? Well, an ion is just an atom with a positive or negative charge, right? What is an ionic compound? Think about that one. An ionic compound is a metal combined with a nonmetal. Now, if you want to get fancy with that definition, you could say an ionic compound is where a metal gives away an electron to a nonmetal and forms an ionic bond. That's pretty heavy though. Let's just say it's metal and nonmetal, right? Next one, how do we name an ionic compound given the chemical formula? So for example, if I give you this, Ca3P2, how could we name that? Think about that. Well, I think first things first, you can notice that calcium, which is Ca, is a metal, and P, which is phosphorus, is a nonmetal. So this is an ionic compound. Ionic compound naming rules just say name the metal and then name the nonmetal. So the metal name is calcium, and I was just checking my periodic table right now. The reason I was doing that is because I want to make sure that calcium is not one of the ones that has more than one charge. It is not, so we just have the metal name, calcium, and then the non-metal name, phosphorus, but we have to change it to ide, right? So it's phosphide, calcium phosphide. Last one here, how do we indicate in a chemical name what ionic charge a multivalent ion, that's one that has more than one charge, has? So if we have TiO2, look at Ti on the periodic table. Ti is titanium. Oops, change slides there, sorry. Ti is titanium. I'm just scanning the periodic table for it. Okay, found it. It's kind of on the left side. Titanium, if I'm just to write this out again, titanium has either a 3 positive charge or a 4 positive charge. So it's multivalent. We have to include that in the chemical name. Oxygen, if you look at oxygen on your periodic table, it only has a 2 negative charge, but there's 2 of them. So that means the overall charge of our oxygens there is 4 negative. So think about what charge this titanium needs to have to balance out 4 negative. Well, of course, it would have to have a 4 positive charge, right? So this would be titanium, and then 4, which is IV, oxide. There it is. Wow. Okay, that was a long lesson. Hopefully we have a few minutes left of class. You can start these questions. I will give you time next class, of course, to polish them off. So don't worry about taking them home. I'll also answer any questions that you have at that time. Hopefully that made some sense today. It might be a lot to absorb right now, but you might want to read just that section of your textbook. Best of luck. I can help you tomorrow.